In this video we're going to consider the relationship between the area of an object and its image that undergoes a transformation represented by a matrix. So here's a statement which tells us about that relationship. It says if an object or region is transformed through multiplication by a matrix T, then the area of the object and its image can be related as follows. And here's the rule or the result, that the area of the image is equal to the absolute value of the determinant of T times the area of the object. So in other words, finding the determinant of the transformation matrix, making sure it's positive, so we might need to take its absolute value, but basically the magnitude of that determinant, that tells us the scale factor, tells us how much the area of the original object has been scaled up or down to find the area of the image. Now that can be proved, and your textbook does a little sort of proof of that. We don't really need to worry too much about that, but you can have a bit of a look if you want. But we can use this, and in some cases it's actually a much simpler way of finding the area of an object or an image. So let's do an example. I might just do one from the textbook. So the first question there from 18G, and it lists a number of parts, so we'll just do the first part. And what it gives us is a matrix representing a transformation. So I'm going to call that T, and for the first part there it's the matrix 3, 1, 1, 1. What it's asking us to do is to consider the transformation that would occur to the unit square under this matrix here. So let's sketch the transformed shape, and then let's calculate its area. So the unit square is, let's start off with our unit square here. I wonder if I've drawn that big enough there. In fact, I might draw it again over this side here. So let's make it slightly larger. There's y and x, and our unit square that we're starting off with is that one there. Alright, so we're going to work out how that's transformed by this particular matrix here. So let's think about the coordinates that we're starting with. They've got 1, 0, 1, 1. We've got 0, 1 over here, and of course the origin, which is 0, 0. So really we're wanting to apply that matrix T as the transformation matrix to each of those points. And we could do each of those individually, so I could sort of do, you know, T times 1, 0 and work out its result, and then T times 1, 1. But I can actually put those all into a single operation. So the vertices 0, 0, 1, 0, 1, 1, and 0, 1, just kind of going around in an anti-clockwise order. So to find image points of each of those, I'm just going to go the matrix T, 3, 1, 1, 1, and basically I'm going to put them all the vertices into a single matrix. I don't really need to do 0, 0 because that doesn't get transformed at all, but I'll put it in there anyway. So there's the 4 coordinate points represented there. And if we go along and do the matrix multiplication now, so the first one will be unchanged, but the second one, if I multiply row 3, 1 by 1, 0, I'll get 3 there, and then 1, 1 times 1, 0 is going to be 1. So I'm just going along and doing my matrix multiplication. 3 times that, that's going to be 4. 1 times that's going to be 2, and then the first row times the last column, that's going to be 1, and the second row times the last column, that's going to be 1 there. So each of these now is represented. Let's get a highlighter and say, okay, well that point, well 0, 0 stayed where it is. So this one here is now at coordinates 3, 1. So let's go 3, 1 there. So I know that's a point on the image, and I know that's where the point 1, 0 has been transformed to. So now I've got 0, 0 joined up with that point there. Let's see if I can get that. Yep, that's where I want it there. The next one, this point here, 1, 1, has been transformed to 4, 2. So 4, 2 would be that point there. And so that's the next side of my parallelogram. Then I have that the point 0, 1 has been transformed to the point 1, 1. And then I guess I just need to join up those two. Alright, so there's my parallelogram represented there. And so that was the first thing that the question wanted me to do, was to actually sketch the image. But the second thing was to find the area of the parallelogram. So area of parallelogram. Well, according to my rule, it's going to be the absolute value of the determinant of t times the area of the original object, which was the square. So the determinant of t, well, it's the absolute value of AD minus BC, which is going to be 3 minus 1. The area of the unit square was 1. So that's the absolute value of 2 times 1, 2 units squared. Now for something pretty simple like a parallelogram, it's probably going to be quicker just to, or if we've worked out what the parallelogram looks like, we can just work out, base times perpendicular height. That might be quicker. But as I say, for some shapes, this is actually going to be a handy way to work out the area of shapes which otherwise might be complex to calculate.